Well, hello everybody. Welcome to University of Montana, GEO 572, Advanced Hydrogeology. Coming to you guys from beautiful Socorro, New Mexico today, and we're going to start talking about solute transport. Okay, so solute transport is essentially the theory and understanding of how things move around in the subsurface. So let's go ahead and start our discussion. I'm going to share my screen here, potentially. And we're going to start our discussion of solute transport by considering just some unit analysis. So just getting some units down. So solute transport units. All right, so the first thing that we're going to define here in our solute transport is the mole, which probably everyone here has heard of. But the mole is basically just a fancy or very large dozen, right? It's the same idea, and it's just a number of things. All right, and that number is 6.02. Rewrite that. 6.02 times 10 to the 23rd things or bits of something. So we could have a mole of anything, a mole of beers, or be a lot of beers, probably not even ever been a mole of beers on the planet yet, but we could have a mole of beers, right? So a mole is just 6.02 times 10 to the 23rd. It's just the number of things. And I'm gonna call the number of things, I'm gonna label that a big N, all right? So anytime we're talking about a number of things, let's call it N, a number. All right, so mole is really just a measurement of a number or amount of things. The next thing we're going to talk about is concentration. All right, and concentration is the amount of solute. Right, and solute is the stuff dissolved inside a solvent. All right, so the solute is dissolved inside a solvent. So for us, most of the time, well, for us, our solvent is almost always going to be water. So e.g. water. Okay, so concentration, we're most commonly going to measure two ways. So one is molarity. Sorry. Molarity. Molarity is the moles of solute per meter cubed of solvent. So we can think about this as the number of things over volume of solvent. Number of solute bits per volume of solvent. All right, molarity. And the big point here is that it's volume. All right. The other one is molality. And this is moles per kilogram of solvent. All right, so this is number of solute particles per mass of solvent. All right, and the key here is that for molality, we're using mass. Okay, so moles, number, concentration, basically just numbers per either volume or kilogram of solvent. It's very important to recognize the difference in those. That difference will become very important later on. All right, so the other thing we're gonna talk about a lot is the movement of solute, all right? So one way we can quantify the movement of solute is by the molar flux. All right, and the molar flux is the moles per time per unit area. All right, so this is the number of solute particles crossing a plane per unit time per unit area. All right, so just like Darcy flux was the volume of water moving across a plane per unit time per unit area, molar flux is just the number of solute particles moving across a plane per unit time per unit area. So one way we can think about flux is that we could think about, for instance, the flux across the flux we could think about thinking about discharge. So as an example, we can get at the molar flux. I'm going to call, oh yeah, let's go ahead and do this. We're going to call the molar flux J. All right. So as an example, our molar flux J, we can write as equal to the discharge of water, right, times the concentration in water over the area. And what do you think the units need to be of this concentration? Let's take a second and decide what you think they might need to be. Well, our discharge is in volume per time, so meters cubed per time. This concentration, if it's molarity, it's moles per meter cubed, all right, times 1 over the area. All right, I just pulled that 1 over the area out over here. And here's what happens. I get the meters cubed canceling, moles per time per area. per meter squared. Let's call area meter squared. All right. Let me erase that, clean that up here. So we end up with the units of moles per time, per meter squared, or per area. That is molar flux, right? So discharge times concentration divided by the area. Similarly, we can write J as equal to Q over A times C. And we can use our definition of Darcy flux for Q over A. So it's equal to little q times C. So the molar flux, Q times C, for flowing water. Or molar flux as a function of the Darcy flux. Okay, so molar flux, this is just an example of a type of molar flux. So we've got moles, concentration, molarity or molality, and molar flux defined. All right, so I want to start talking more about solute transport methods. And the first of those methods that we're going to talk about here today is diffusion. Okay, so this is an introduction to diffusion. So let's imagine that we've got a theoretical plane here. All right, so we got a plane and we've got a bunch of dissolved stuff. So these little green bits are dissolved things in water. And they're on either side of the plane. All right, and these dissolved bits are moving around randomly, as anything does when it has a temperature. All right, so these dissolved bits move around in a random motion. And if things are constant temperature, they move a fixed length delta x over a time span delta t. So if our temperature is constant, delta x is the same for all these particles, is equal for all particles. They have the same mass, and these are all the same stuff. So they all have the same mass for all particles for a given delta t. All right, so we got all these things moving around randomly. And what we're interested in is the flux, or the net movement, the flux of particles across our plane, right? That's what we want to figure out, a molar flux due to diffusion. All right, so it stands to reason that the number of particles that'll cross my plane, let's say from the, let's have a left side and a right side. So the flux of particles across my plane from left to right All right, that's the number of particles that move from this side to this side across this plane. It stands to reason that it's proportional to the number of bits within delta x from my plane, right? If you can move delta x, then the number of bits outside of delta x doesn't really matter, but the number of bits within delta x does matter. So we might write this as the number of bits on the left within delta x. All right, that's left to right. And by similar reasoning, we could say the flux from right to left is proportional to the number of bits on the right within delta x. All right, so how many bits are within delta x on this side of the plane? So the net flux, all right, the total flux, it would be the flux of particles moving across from this minus the particles that move across from that side. The net flux is J is F, oh, sorry, is J left to right minus J right to left all over. And then if we substitute in these guys here and these guys here, we get J is equal to the number of bits on the left over minus the number of bits on the right all over delta x. And this should be a proportionality. All right, so this statement right here, that the flux is proportional, the number of bits of the left minus the number of bits to the right over delta x. Well, this guy here is essentially the gradient in the number of bits. And if each one of these has a volume of delta x by delta y by delta z, there's a volume on either side of this, we can basically surmise that the flux is proportional to the concentration gradient, dc dx, all right? And that's just saying the number of bits in some volume, delta x by delta y by delta z. All right, the number of bits here, and we got the same volume on the other side. We can turn these number of bits then into a concentration, right, into molarity very easily. And we can intuit that the net flux here from this random motion is proportional to the gradient, or the difference in the bits in these volumes, or the gradient in the concentration. And this turns out to hold. All right. So this is the intuition for Fick's first law of diffusion. And Fick's first law is that the flux, J, of particles across my plane is equal to d, negative d times dc dx. And I'm going to This is the flux across our plane. In the x direction, and it is proportional to the concentration gradient in the x direction, and it has a constant of proportionality d. We're going to get way into, but this d is the diffusion coefficient. Okay, so let's take a step back and let's look at the form of this. And let's recall another law that we've talked about. Q is equal to negative k dH dx. You see, Darcy's has the exact same form. This is Darcy's law. And Darcy's has the exact same form as Fick's first law. The flux is equal to some constant proportionality times the gradient. All right? Here it's the head. In Fick's law, it's concentration. So the exact same form, Fick's has the same form as Darcy's. All right, so here's one first good news. All the solutions that we've talked about for Darcy's law, right? Everything, all our intuition for Darcy's law now holds for Fick's law. Okay. So now I want to look a little bit. Fusion doesn't have two S's, so first of all, let's fix our diffusion coefficient here. Diffusion is right. Doesn't have two S's. Diffusion coefficient. Okay, now I want to focus in on the diffusion coefficient. So let's consider some porous media. So we've got a bunch of grains, sediment grains here. And if I am a diffusing particle, all right, so let's say I'm these diffusing particles and I'm randomly moving around through here, but I'm working my way through the porous media. We have some important things to note, and that is that our diffusing particles cannot travel through our grains. They have to move around the grains. So diffusing, and really particles moving by any method, but here we're talking about diffusion. So diffusing, God, why do I keep putting two S's on there? Diffusing, diffusing particles have to move all the way around. So must move around. Grains. all right? And that makes the path. So, you know, we often think of length. We are going to have a coordinate axis that looks like this oftentimes, right? Oh, that's terrible, but you know what I mean. X, Y, and Z. And so the path, the straight line path here from this end to this end here is delta X, but the path that the particle has to take is much longer and it's delta L, right? So there's two things that the grains do. First of all, they make the path longer, and that the only area across which diffusion can occur. So if I have some plane here, right? I got some plane what we're interested in diffusion across. Okay, the only area available for diffusion is through the pore throats. So the area available for diffusion is the pore throats only. So this leads to a couple things. So in free water, we have a diffusion coefficient that is set the free water diffusion coefficient basically tells us it's a function of how far the particles can move. So it's a function of the particle size and temperature, but it's also a function of the molecular spacing of water because it's going to run into water molecules. So free water diffusion coefficient basically tells us how fast things can move in free water alone. So how fast diffusion occurs. It's a measure of the ease of diffusion in water alone. Let's put it that way. It's not really the speed, but it's a measure of the ease of diffusion in water alone. Well, so in a porous media, the atom is moving by the free water diffusion coefficient in the pores, but we are looking at sort of diffusion through this pore network. And we're not considering the individual pore throats. So we're going to call the free water diffusion coefficient DD for the molecular diffusion coefficient. So in a porous media, we have the effective diffusion coefficient. We'll call it D star. And I'm going to number these processes. The effective diffusion coefficient, because of one, is something like this. It's equal to omega times dd, where omega is proportional to the tortuosity, all right? And here the tortuosity, I'm going to define as delta x over delta L. All right, so delta L is our travel length, delta x is the straight line length, and tortuosity is sort of the measurement of the difference between the two. All right, so the more the path has to move crazily around particles, delta L gets really long, delta X gets really sharp, so my tortuosity gets lower and lower. All right, so my effective diffuse, so tortuosity will always be less than 1, or omega defined this way. If I define tortuosity this way, omega will be less than 1 because delta L will always be longer than delta X. And my effective diffusion coefficient will always be less than my free molecular diffusion coefficient. So one example of trying to estimate W or tortuosity is with Archie's law. And Archie's law says that our effective diffusion coefficient is equal to the porosity N to some exponent M times the diffusion coefficient in free water. So reminder, N is porosity. And M is some fitting parameter. So that says that omega is proportional to the porosity to some, or omega is defined here in Archie's law as the porosity raised to this power m. And in many cases, these fall between n squared to n to the 0.5. All right. So Archie's law gives us some intuition that the tortuosity is proportional to the porosity. The smaller the porosity, the more tortuous the material. Okay. So Fick's first law of diffusion is governed by this parameter, effective diffusion coefficient. So let's rewrite Fick's first law now in porous media. So Fick's first law in porous media. Uh-oh. I know what this means. We've got to get this puppy to sync again. Okay, so Fick's first law in porous media says this. J is equal to d star, negative d star, times dc dl. All right, so this is just a generic flux in some direction is equal to the effective diffusion coefficient in the porous media times the concentration gradient. All right, so now let's derive the diffusive mass transport equation. All right, and so we're going to derive this using the continuity equation. So I'm going to draw a very special block of porous media. I'm going to start over again because my lines are not straight. And remember, this very special block is called the REV, the representative elementary volume. All right, and our REV has particles or grains. So it's a porous media, REV. All right, so here's our REV of porous media, and its size is delta X by delta Y by delta Z. All right, look familiar? All right, so let's do the diffusive mass balance equation. So mass balance for solute. So we have J in, and we're going to do X direction only. This is J out. All right, fine. We could write that as J in plus dj dx times delta x. Okay, so let's look at the mass balance. Well, the total number of, so total moles in the box in our box would be the concentration in moles per volume, so molarity, concentration, let's do it this way. Let's start off this way. The total moles in the box would be the number of moles, all right, number of bits per volume of the box times the volume of the box, delta x, delta y, delta z. All right, but what is the total volume here that water can be dissolved? It's not the total volume of the box, because that's the total volume of porous media. The volume which stuff can be dissolved in is the water-filled volume. All right, so we have to multiply this by porosity. Multiply it by the porosity. All right, so the total volume in the box is really N. Well, the number of moles divided by the volume, that's the molarity. So I'm going to just write that C, where C is moles per volume, molarity, times delta X, delta Y, delta Z. All right, so the change in that versus time, we're going to say is the change is equal to the flux in minus the flux out, just like Darcy's law. So mass balance gives us this, N, delta X, delta Y, delta Z, times dC dt, the change in concentration over time, is equal to J in minus J out times delta X times, times delta Y times delta Z, so times the area, times the area across which the flux is occurring, so delta Y times delta Z. All right, and I can rewrite that as J in minus J in plus dJ dx times delta x times delta y times delta z. All right, and if I do some arithmetic here, I end up with n delta x delta y delta z is equal to negative dj dx. Let's label this with x. djx dx times delta x, delta y, delta z. Oh, this is, sorry, dc dt. All right, so we can do the same process. So this is for x direction. So for all directions, we do the same thing for each directions. And we're going to get the continuity equation, n. Oh, these cancel out these volumes up here, sorry. So I get n dc dt is equal to dj dx. So n I forgot something very important. Forgive me. The area across which diffusion can occur. What have I assumed here? When I wrote just delta y, delta z, I said, hey, the flux of solutes is occurring over all of this area, but it is not. It is only occurring through the porosity. So I need to multiply by n, the area here. And I have n here. Okay, so now N cancels out here, and I get dc dt is equal to negative dj dx minus djy dx minus djz dx. All right, and now substitute in Fick's first law for j. And I get dc dt is equal to d dx d star dc dx plus d dy d star dc dy d dz is equal to d star dc dz. All right, so this is my mass transport equation for diffusion. This is my diffusion equation. And I hope you can see here that it is almost completely analogous to the groundwater flow equation. So here, instead of dH dt, we have dC dt. We don't have a storage term because the porosity fell out. All right, but we have dC dt is equal to the gradient of the flux. All right, so this looks just like the head equation, except now H's are replaced with C's, and instead of K, I have D star. So finally, if D star is constant in space, i.e. homogeneous, I can pull it out and I get dc dt is equal to d star d squared c dx squared plus d star. Let's just get d stars the same and the same in all directions. This, by the way, is true in a fluid, but not in a porous media. But for simplicity, let's just do this. Let's say it's homogeneous and isotropic. And this form here is often called Fick's second law. That says the change in concentration with time is equal to the diffusion coefficient times the curvature of the concentration. So the Fick's second law is really what I would call the diffusion equation, but it's the same thing. All right, so this is the diffusion equation. So here's the cool thing. All of our groundwater flow solutions, for instance, the instantaneous step change in head, we had an analytical solution for that. Well, it'll work for the diffusion equation. So here we might have an instantaneous step change in concentration, all right? And we can look at how that concentration change propagates diffusively through a media. All right, so that brings us to a close on diffusion and deriving the diffusion equation. In the next go around, we're going to talk more about advection. So this diffusion is completely independent of the movement of water, right? It's just random molecules moving around. In our next lecture, we'll begin talking about advection and movement of water by fluid moving or through the fluid velocity. All right, thanks for attending, and we'll talk to you soon.